Scientists just solved one of quantum computing's biggest problems using a one-way street. Source: RIKEN research. Imagine standing in a room filled with hundreds of pendulum clocks. At first, every clock swings at its own rhythm. But after some time, something remarkable happens. Without anyone touching them, the clocks begin moving together, perfectly synchronized, as if they are communicating through invisible forces. This phenomenon, known as synchronization, appears throughout nature. Fireflies flash in unison. Heart cells beat together. Even distant stars can exhibit synchronized behavior. Now imagine achieving something similar inside a quantum computer, where particles obey the bizarre rules of quantum mechanics. Scientists believe quantum synchronization could become one of the keys to building faster, more stable, and more reliable quantum technologies. But there has always been a problem. Real quantum systems are incredibly fragile. Tiny manufacturing defects or even the slightest environmental noise can destroy the delicate quantum behavior they depend on. Now researchers at RIKEN have proposed an elegant new solution. Instead of making quantum systems synchronize in both directions, they have created a way for synchronization to occur in only one direction, like a one-way street for quantum sound particles known as phonons. Even more surprising, the effect remains remarkably stable despite imperfections that would normally ruin quantum behavior. If confirmed experimentally, the discovery could provide a new foundation for practical quantum computing and quantum communication. To understand why this matters, we first need to understand synchronization. Synchronization happens whenever separate systems naturally begin behaving in the same way. If you've ever seen a crowd clap in perfect rhythm, or watched a group of metronomes gradually fall into step, you've witnessed synchronization in action. In classical physics, synchronization is everywhere. Quantum mechanics, however, is a completely different world. Quantum particles exist in delicate states that can disappear the instant they interact with their surroundings. Creating synchronized quantum behavior is therefore much more difficult and much more valuable. Researchers believe synchronized quantum systems could improve quantum sensors, communication networks, and future quantum computers. But making quantum systems synchronize reliably has remained one of the field's biggest challenges. Another concept plays an important role in this story: non-reciprocity. The word sounds complicated, but the idea is surprisingly simple. Imagine driving down a one-way street. Cars move freely in one direction, while traffic from the opposite direction is blocked. Many modern technologies already rely on this principle. Optical isolators allow light to travel forward while preventing reflections from traveling backward. Microwave circuits use one-way components to guide signals efficiently. These devices improve performance and reduce interference. Scientists have long wondered whether the same idea could be applied to quantum synchronization. Could one quantum system influence another without being influenced in return? That is exactly what researchers call non-reciprocal quantum synchronization. Unfortunately, previous proposals suffered from a major weakness. They worked beautifully in ideal theoretical models, but became extremely fragile when exposed to the messy reality of manufacturing imperfections and environmental noise. This is where the new RIKEN proposal becomes so interesting. The researchers developed a theoretical framework that combines two separate quantum effects into a single system. The result is surprisingly elegant. When light or a magnetic field is applied from one direction, tiny sound particles called phonons become synchronized. Apply the same influence from the opposite direction, however, and synchronization simply does not occur. The system behaves like a quantum one-way street. Information flows one way, but not the other. This directional behavior could give engineers far greater control over quantum devices while reducing unwanted interactions that introduce errors. But the biggest surprise came when researchers tested how robust the system was. Normally, quantum effects are extremely sensitive. Tiny defects created during manufacturing or random environmental fluctuations can quickly destroy fragile quantum states. These limitations are among the biggest obstacles preventing quantum computers from becoming practical. Yet the proposed synchronization mechanism continued working even when substantial imperfections and noise were introduced. The researchers were surprised to find that synchronization survived conditions previously believed impossible without complicated protection techniques. That robustness could be a major breakthrough. Instead of requiring increasingly complex error correction systems, future quantum devices might naturally resist many sources of disruption. At the center of this discovery are phonons. Unlike photons, which are particles of light, phonons represent tiny packets of vibrational energy, the quantum particles associated with sound. Inside solid materials, atoms constantly vibrate. Those vibrations behave collectively as phonons, carrying energy and information through crystals. Scientists are increasingly exploring phonons as information carriers because they can interact strongly with other quantum systems while operating at extremely small scales. Controlling phonons with one-way synchronization could open entirely new possibilities for quantum engineering. The implications extend well beyond quantum computers. Quantum networks may eventually connect distant quantum processors into a quantum internet capable of transmitting information with unprecedented security. Reliable synchronization between quantum nodes will be essential for making those networks practical. The same principles could improve quantum sensors capable of detecting incredibly small changes in magnetic fields, gravity, or motion. Perhaps most importantly, robust synchronization could become another building block for fault-tolerant quantum computing. One of the biggest obstacles facing today's quantum processors is error accumulation. Every unwanted interaction introduces mistakes that limit computation. By allowing information to flow in only one direction while resisting noise, nonreciprocal synchronization could help reduce those errors naturally. The work remains theoretical for now, and experimental confirmation will still be needed. But the idea represents an important shift in quantum engineering. For years, researchers have searched for increasingly complicated ways to protect fragile quantum systems. This study suggests that smarter architecture, not simply greater complexity, may provide a better solution. Sometimes the best way to control a quantum system is to give it fewer directions to travel. A simple one-way street for quantum sound may ultimately become one of the keys that unlocks reliable quantum technologies. And if that happens, the future of quantum computing may depend not only on making quantum systems more powerful, but on teaching them which direction